Good morning, grade 11s. Today we're going to be looking at current electricity, but specifically I'm going to revise what you did in grade 10 with current electricity, including the bit about EMF and internal resistance. Now, I first want to make it very clear that internal resistance and EMF is actually matric work. We do it already in grade 10 so that by the time you get to matric, it's super duper easy work to do. So it's all about good practice and getting it right now. So in your grade 11 textbook, we're going to be working from page 345 to the end, but a lot of this won't be in the textbook. So the EMF stuff won't be in the textbook. You can use these notes. Again, the PowerPoint is available on the school's website, and I have sent it to the WhatsApp group. And especially if electricity is something that you struggle with, I really think you need to do the whole of exercise 19 on page 355. Make sure you have the basics right so that you can work on then getting EMF and internal resistance right. Now, you'll see there's one other section that we do in grade 11 on graphs. Ohm's law, specifically the graphs of Ohm's law. That is new work, and I will thus cover that content in class. Right, if you look in your definition book on the page that says electrostatics, electromagnetism, and current electricity, the third little bit at the bottom, a whole 6 definitions on electricity is really all that you can get asked about, which is nice. I think probably the most common one they ask in grade 11 is for Ohms to state Ohm's law. And please don't forget the part where you include that it's at a constant temperature is very important in the Ohm's law definition. If you look here, I've put the information sheet up. All your electricity definitions, equations are on the information sheet. This is actually the matric information sheet because it includes the EMF equations, but the grade 11 one looks pretty much exactly like this, just without the EMF definitions on it. So if we start on electricity, one thing we learned when we did chemistry now, we learned about a metallic bond, where we said a metallic bond is a positive nucleus surrounded by a sea of delocalized electrons. The blue dots in the picture here are the electrons. So what happens because these electrons are delocalized? The power source, aka your cell or battery, can submit or give power into the energy into the circuit via these conductors, which have metallic bonds, and the electrons get energized. Then the electron passes it on to the next electron and passes it on to the next electron, and this obviously happens super fast. And hence we talk about our metals as being conductors. Right, so the energy gets passed on from one electron to the next. An ammeter measures the rate at which that happens. So it's literally like the ammeter's chilling in the circuit going, right, energy's passing, more energy, more energy, more energy, more energy. So hence we talk about I, the current strength, being equal to Q over T, so the rate of flow of charge in the circuit. Ammeter is in series in the circuit, so it has a very low resistance, so it really doesn't influence the resistance of the circuit. And remember, we measure this current strength in amperes, which is just an A. Please don't write amps. That is such a non-thing to write. It's A, or it's the whole word, amperes. Right, so if you look at this circuit, you can see it is a series circuit, so the ammeter reading is going to be the same everywhere in the circuit. If we look at a voltmeter is always connected over a resistor or over the cell, as it measures the difference in potential energy before and after. Hence, we refer to it as potential difference. It has a very high resistance, so the current won't choose to flow through the voltmeter. It will still go through the resistor or through the battery, and the voltmeter can just measure the potential difference. Right, if we look at resistors in series, the simple formula, the total resistance would be equal to R1 plus R2 plus R3. So in this case, it would be 4 plus 6 plus 8, which would be a total of 18 ohms. And what we need to remember is resistors in series are voltage dividers but the current stays the same. So what does that mean? If the battery over here has a potential difference of 12 volts, and just remember, even if there's no voltmeter, there's still a potential difference between the start and the end. It's just not specifically being measured. So no voltmeter there, but the battery is still a 12-volt battery as said over there. Because those two resistors are each 3 ohms, the 12 volts is divided equally between the two resistors. Hence, each reading on those 2 voltmeters would be 6 volts. Remember, the current stays the same everywhere in the circuit. However, if we look at this circuit where the one resistor is 6 ohms, the other resistor is 3 ohms, the 6 ohm resistor will receive more of the 12 volts than the 3 ohm resistor. If we just use straightforward mathematical ratios, the 6 ohm resistor will receive 8 volts, whereas the 3 ohm resistor will only receive 4 volts. But do you see, still 8 plus 4 is 12, because the divided amongst the resistors in series. And once again, we have to remember the current strength of the ammeter reading will stay the same everywhere in the circuit. Right, resistors in parallel, that's a slightly more complex equation because it's 1 over R1 plus 1 over R2 plus 1 over blah, 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 however many resistors there are. And just remember though, we don't want 1 over R as a final answer. We want R over 1. So in other words, you have to turn it around. If we look at this example over there, it is always important to write down the equation. So here, 1 over R, if you write 1 over RP or 1 over RT, or for total P for parallel, or draw 2 parallel lines, it really doesn't matter which one you use. But you always have to write down the equation. Remember, no equation, no marks. Then you have to show the substitution. So you have to write in this example 1 over 2 plus 1 over 3 plus 1 over 4. Then you can skip those steps because I know you can do the rest of it on your calculator. But it's very important you then say R parallel is equal to, and the final answer here is 0.92 ohms. Just remember, if there's a circuit that has both a series and a parallel combination, you need to do the parallel combination separately on its own. Mathematically, this is correct. So for this example, it's 6, 8, and 4. We'd get the total parallel combination as 1.85. And what we are saying over here, grade 11s, is that we are finding a single resistor which has the same effect as those 3 resistors combined. Let me say that again. When we're working out a parallel combination, we are finding a single resistor which has the same effect as the 3 resistors combined. So having a 6 ohm and an 8 ohm and a 4 ohm in parallel is the same as just having a single 1.85 ohm resistor. Then the second part, we've got to add it to the 6 ohm resistor, which is in series over there. And again, you have to have an equation. Please, R total would be R parallel plus R series. So 1.85 plus 6, which gives us a total resistance of this circuit of 7.85 ohms. So again, what we've done over here, we've said with all these resistors in the circuit, if we were to replace it with a single resistor, the value of that resistor would be 7.85 ohms. Right, remember as well, resistors in parallel are current dividers, but the potential difference stays the same in that parallel component. So let's just confirm everything we have learned. We've learned about resistors in series, and we simply add them together. R total would be R1 plus R2. We've learned about resistors in parallel, and we've said that if we're working out the resistors in parallel, we are basically working out what a single resistor would be with the same value. If we look at voltmeters in series, they add up to give us the total voltage over the battery. So if we look here, V1 plus V2 would give us V in that scenario, in that circuit over there. However, we have said that voltmeters in parallel remain the same. So if we look at where V2 is, pardon me, if we had another voltmeter over the other resistor, or we had a voltmeter over that whole parallel combination, it would give us the same answer because the voltmeters in parallel stay the same. But V2 plus V1, because those two are in series with each other, add up to give us the total V. Ammeters in series, simple, they are the same everywhere. So any part of this circuit except that little parallel combination would have an ammeter reading of 2 amperes. However, in parallel, our ammeter reading divides. So if we look here at A2 and A3, in this example, they would each be 1 ampere because both resistors are 2 ohms, so they would divide equally. However, if we look at it, let's say the one was 4 ohms and the other one was 2 ohms, the 4 ohm resistor would have less current because, you know, the current really doesn't want to go through the difficult high resistant path. It wants to go through the easy 2 ohm path. Okay, I think we've got that. The next thing we need to learn is Ohm's law. I know it's a law we've learned before, so let's just quickly say it and revise it and learn it off by heart. It's another one that's very commonly asked. Remember I said in class about Newton 2 being common? This one's also pretty common. Ohm's law says the potential difference over a resistor, because remember we measure potential difference over the resistor or over the battery or over the conductor, is directly proportional to the current flowing through the resistor, provided the temperature remains constant. So do you see in Ohm's law, we don't mention resistance. All we are mentioning is the relationship between the potential difference and the current if the temperature remains constant. From that, we get the equation where we say R is equal to V over I.